All right, we're going to start by looking at number 26 in the homework, which says, sketch two periods of the graph and identify the stretching factor, the period, and the asymptotes. All right, we're looking at this one down here. F of x is equal to pi times tangent of pi x minus pi. Goodness, that's a lot of pi. All right, and so we're going to need to graph it, and we're going to need to identify the important things. Okay, so let's get this ready to go. Let's graph it over here. And let's plot it. Pi times tangent of pi x minus pi minus pi. Goodness. Pi times tangent of pi x minus pi minus pi. All right, and let's get the right scale. So first off, let's look at our period. Our period is positive 1, right? The difference between these x coordinates is positive 1. So let's make our step size over here. Positive 1, hit that little wrench icon. And let's look from maybe negative 2 to positive 2. We only need 2 periods of this. All right, so maybe we could start at like negative 1. All right, this is what we have going here. Our asymptotes seem to be at negative 1/2. Actually, it seems to be at these ones, right? They're already ready for me right here. Okay, and then there seems to be a vertical shift as well. Well, we know there's a vertical shift, right? We know it's negative pi. And in fact, since our stretching factor is pi, our y-coordinates, we want those to have to do with pi, right? So the whole idea about stretching factor is normally at this like halfway point, at this halfway point between the middle and the asymptote, we normally go up 1, but now we're going up pi. So it actually makes a lot of sense to have our y-coordinates in terms of pi. Now look at this. Our middle is at negative pi. When you go halfway up, we go up positive pi, right? Negative pi to positive 0. That doesn't make sense. Negative pi to 0 is a difference of positive pi. That's that stretching factor kind of getting reflected here. And this is kind of what we have to go on to graph. All right, and again, this is another one of those situations where there's a phase shift, but the phase shift turns out to be 1 here, which is also the period. So we actually don't have to worry about the phase shift. And again, you could get rid of that phase shift, and it's the same exact graph. Okay, let's kind of start incorporating this data. So we're going to divide, our period is going to get divided into 4 boxes. All right, just like sine and cosine. Period is going to get divided into 4 boxes. So our period here is 1. Right, period is 1. Let's maybe make a note of that. Period is 1. So let's have 1 count as 4 boxes. This is 1. And this is 2. And this is negative 1. The y-axis, we're going to scale in terms of pi, just like it's done over here. So let's do it exactly the same, where 2 boxes is pi. Let this be positive pi, and this be 2 pi. Again, we're picking a scale that makes sense so that we can see things more easily. The period is 1. Let's mark these asymptotes. They're at 1/2, negative 1/2, and 1.5. Negative 1/2, positive 1/2, and 1.5. Good. And if you wanted, you could also kind of look at, hey, this is all shifted down negative pi. So this is actually where our middle is going to occur, right? Because we're going down pi units. So our middle is at 0, negative pi, right? That's right here. And then normally, if we go halfway, a quarter of the period, if we go halfway to the asymptote, normally we go up 1, but we're getting stretched. So we also have this point, which is at 1/4, 0. And it's symmetric. We also have this point down here. Copy the period over. We only need to graph 2 periods here. And we have this. Should fill this in with the shape. And that's what you get. Now it also wanted what other information did it want from us? It wanted a little bit more. Stretching factor, period, and asymptotes. So the stretching factor is the absolute value A, which is pi here. And the asymptotes, I guess I also did the asymptotes in red, but whatever. Asymptotes are x equals, always x equals. They're vertical lines. Vertical lines have the form x equals. X equals, pick any one you want. 1/2, sure. Plus, now we put the period. The period is 1 times k. This is actually the same. Did I already do this problem? This looks very familiar to me. Did a similar problem, but not the exact same problem. It has a similar answer. But those are the asymptotes. And this is for k is any integer. There we go. We have our graph. We have the other answers, and that's problem number 26. Next, let's look at 38. Now 38 is asking us, find and graph 2 periods of the periodic function with a given stretching factor, period, and phase shift. So, okay, it's going to be tangent, which means it's going to be of this form. And what does it tell us? It tells us that A is -2. Period is pi/4. And phase shift is the point HK is at -pi/4, -2. All right, we need to find and graph 2 periods of the periodic function with this information in mind. All right, so this is giving us the shift of the horizontal shift. I haven't really mentioned it before. The horizontal shift and the vertical shift. This tells us like the middle, the start of our graph. So if you wanted to, you could come up with an equation for this. Or you could just directly graph this by hand. 2 methods. Let's try directly graphing it by hand. Coming up with a formula also works. But I think this is going to be useful to kind of show another point of view here. Goodness, I'm getting a lot of emails while recording these videos. So normally we divide the period. Let's say the period is always 4 boxes. We almost always do that. Okay? So period is pi/4. So let's say this is pi/4. Another 4 boxes is another period. Another pi/4 brings us to pi/2. And 4 boxes in the other way is going to be -pi/4. All right. Now the phase shift is kind of where we have to go next. All right. The phase shift says we're shifted left pi/4. Oh, well, we can ignore this basically, right? That horizontal shift is the period. So we can ignore that, right? Shifting something over by a period doesn't really matter. But I'll show you what happens anyway, right? If we're moving left pi/4 and down 2, okay, Down 2, a is also in 2, so it actually makes sense to have things in terms of not pi's for the y-axis. Let's have things be in terms of 1 or 2. Okay, but we're moving, yeah, it's fine to just count by ones. If we counted by ones and we have to change it later, that's fine. All right, so our new middle of the graph is negative pi over 4, negative 2. And then it's periodic every pi over 4. So every 4 boxes, it repeats. Let's use blue again, be consistent. Every 4 boxes, this repeats. We only needed to draw 2 periods, but I guess I'm drawing 4 maybe, or part of 4. And then the asymptote is always halfway along. So we know the asymptote has to be halfway between each of these middles, right? The blue dots are the middles. Note that the asymptote is repeating every period, every pi over 4. Now the stretching factor is going to be the hardest thing to include here, but it is also going to be the last thing that we have to do. Normally tangent, if you go 1 box over, a quarter of the period, you go over 1, normally tangent goes up 1. But a is negative 2. So instead of going up positive 1, we're actually moving down 2. Normally when we go to the left, we would go down 1, but because a is negative 2, we're going up 2. And that's how you incorporate the stretching factor here. And what we're going to get is a negative tangent graph, which actually is like cotangent, but we're not really going to talk about cotangent graphs that much. And we get something that looks like this. And again, we could draw as many periods as we want. We only needed 2. We drew extra. And I think that's everything that it wanted us to do. Graph 2 periods, given stretching factor, period, and phase shift. And there we go. We did it. Let's do one more problem in this video, number 54. I actually don't think we need the graph paper for 54 if I remember what it is. Oh, I don't remember what it is. The function f of x equals 20 tangent of pi over 10x. Let's write that down. F of x equals 20 tangent of pi over 10x marks the distance. All right, the distance f of x is in feet. This is distance in feet, and x is time in seconds. In the movement of a light beam from a police car across the wall for time x in seconds. So again, let's kind of think about this real quick. Let's get a visualization here. Anytime you're doing an application problem, you want a visualization. You want to know what you're looking at before we even try to do this problem. So there's a police car. This is what police cars look like. And it's shining a light on a wall. All right. So at different times, right? So the police car light is rotating in a circle, right? So there's one point, it's shining like directly across, right? And then later it's shining over here. And as time goes on, assuming that light can go infinitely far, and which I'm pretty sure it can, and the Earth is flat, which I'm pretty sure it isn't, but if we assume that, then this distance, right? Specifically, what is this distance? The distance in the movement of a light beam from a police car across the wall. So basically it just means what is the distance from where the light hits to this point. Okay, that's kind of what's being illustrated here. Whoa, our wall. And holy moly, I wonder if something's going on. I'm getting 5,000 emails today. I guess I'll check them after this problem. Hopefully it's nothing important. All right, let's see what we have here. So this is our function. Part A, graph on the interval 0 to 5. Okay, so let's go to Desmos and graph this function. Function is 20 times tangent of pi over 10 times x. I think that was the function. It is, good. Let's get rid of these old asymptotes. And we want to plot this from 0 to 5. Let's plot it a little further than we need to. And let's make the y-axis scale big enough so that we can actually see what's going on here. We're going to need more. Yeah, something like that. Well, 0 to 5. We need to make it bigger. Goodness, how big does y need to be? Still can't see it at 5. You know why? Because it's an asymptote. No matter how high we make this, we're never going to see how big it is at 5. Because it's never going to hit 5. All right, it's just going to keep getting bigger and bigger and bigger. So let's just say 200 is enough. Not Q100, I said 200. All right. And this is what we have. And which makes sense because it's actually not the distance from this point. I think it's the distance from the car. No, it is the distance from this point. Yep. Distance from this point up here. And then as time goes on, the light moves further and further and further. That distance increases. Not quite exponentially, but that similar exponential shape. Tangentially. Okay. So that's what it looks like. For the other ones, I want you to plot them by hand. But for this one, you don't really have to plot it by hand. I'll try to be very clear on what I want plotted by hand and what I don't want plotted by hand. Usually, I want it plotted by hand, but let's not worry about it for this application problem. Where is the problem? Part B, find and interpret the stretching factor, period, and asymptote. All right, so we're going to need the stretching factor. We're going to need the period. And we're going to need the asymptote and an interpretation for what these represent. So the stretching factor is the absolute value of A. Whoa, wrong color. The absolute value of A, which is 20 here. The stretching factor is 20. We need to interpret that too, but it's not really clear what that means just yet. So let's wait a little bit. The period is going to be pi divided by the absolute value of B, which is pi divided by pi over 10, just pi over 1 times the reciprocal, 10 over pi. Pi's cancel, the period is 10. Let's also wait to interpret that one as well. The asymptote, that was very clear from the graph. Well, took a little bit, but it should have been very clear. The asymptote is at x equals 5. Okay. So let's try to interpret each of these things now. The asymptote, what is x? X is time in seconds, which means as we get really close to 5 seconds, this light is getting so far away, right? As it gets really close to 5 seconds, the light is shining so, like, infinitely far away. Infinitely far away would be almost parallel to the wall. So specifically at 5 seconds, that's where the asymptote is. At 5 seconds, it's going perfectly parallel to the wall. It's not hitting the wall at all. That's why it's undefined. But like a split second before, it's just going really close to parallel and the light's going really, really far. Okay? We can say at 5 seconds, the light is parallel to the wall, or going parallel, moving parallel. because light is moving, right? It looks instantaneous to us, but it does have a travel time, namely the speed of light, which is why it's called that. Period is 10. Period of 10 means that these lights, it takes 10 seconds for the light to move all the way from going to the left to all the way from going to the right. Okay, and again, this is one of those cop car lights that is light on both sides. So it takes 10 seconds for the light to rotate 180 degrees. Stretching factor now. So stretching factor has to do with the y values. So normally, if we go a quarter of the period, halfway to the asymptote, either way it's 2.5, we go 2.5 seconds, normally we'd move 1 foot, but we're moving 20 feet instead. Okay, so there's a couple of not great ways of explaining this, but I would say we move 20 feet in 2.5 seconds. Is one good interpretation of the stretching factor. There are probably other good ones as well. That's going to be our answer for part B. Now there's also a part C that we should talk about before I figure out why I'm getting assaulted by emails. Evaluate f of 1 and f of 2.5 and discuss the function's values at those inputs. So f of 1, again, our x value is time, and our y value is distance from this point. So after 1 second, how far are we? And there's two ways of doing this. If you want to be really exact, what you can do is you can just go over here and type in x equals 1. Desmos is helpful with that. It tells you right where these things cross. So after 1 second, we're about 6.5 feet along the wall. Let's approximate. Actually, the second one isn't going to be approximated. F of 1 is about 6.5, means after 1 second, the light has moved 6.5 feet down the wall. So kind of like now the light's going over here, and this distance right here is 6.5 feet. And similarly, we already said that we move 20 feet in 2.5 seconds. This is going to be 20, which is almost the same, right? After 2.5 seconds, the light has moved 25 feet or 20 feet. And you could also look at this on the graph, right? If x is equal to 2.5, this intersection should be at 20, which it is. All right. That's the answer down there. That's the answer to this problem. Time to figure out what is going on with the emails. And if you're curious, I might update you in the next video on 8.3. All right. Have a good one. Let me know if you have any questions.